Hello and warm welcome to everyone to the 26th lecture on the financial econometrics. Today we will be discussing about two common processes of this family ARIMA modeling, that is AR, which stands for autoregressive process, MA, which stands for moving average process, and we will be also discussing the stationarity conditions of an AR process and some statistical properties of the autoregressive process. This autoregressive and moving average process could be represented using these two different equations. Here the first equation shows the autoregressive process, whereas the second equation shows the moving average process. So what we mean by the autoregressive process? So basically autoregressive model or process is one where the current value of the series depends on its past values plus the error term. That is one of the simplest autoregressive process is the AR1 process. So here yt is equal to mu plus phi 1 yt minus 1 plus ut. So here the mu represents the constant, that is basically it shows the mean associated with the series. Phi 1 is the fixed parameter which basically shows the weight through which yt is related with yt minus 1, and ut is the white noise process with mean 0 and variance sigma square. What we mean by the order, so the highest time lag associated with the autoregressive process is known as the order of the autoregressive process. So here this highest lag is the yt minus 1, so that's what we call it autoregressive process 1. The absolute value of phi 1 is less than 1. So we can say that here this autoregressive process for order 1 reflects that the time series behavior of yt is largely depends or determined by its own past values of the series. So what will happen with the current observation is very much determined by its past observation. AR1 process we have written here like this. So for the simplicity, here we will drop mu, we will set that mu is equal to 0. So that is the mean becomes 0. Then we can write this equation as yt is equal to phi 1 yt minus 1 plus ut. Actually, from the previous lectures on the ordinary least square, you can relate this is nothing but the intercept becomes 0. So when the intercept becomes 0, the properties of model usually did not change. So this we can say if we have to draw a regression of with this, so it will be like this. On the other hand, for this it will start with the 0. So basically the intercept here, this is nothing but mu. So the mean of the process is basically we set it is equal to 0. However, it did not change the properties of the data generating process. So using the lag operator and with the successive substitution, we can write equation 1 as follows. That is, we can write it as phi 1 into yt minus 2 plus ut minus 1. Basically, from the lag operator, what we know, if the yt is equal to phi 1 yt minus 1 plus ut, if you take the lag, so we can write yt minus 1 is equal to phi 1 and here yt minus 2 plus ut minus 1. So basically then we have substituted this value with this particular value in this equation. So here we have phi 1. Now in place of yt minus 1, we write this particular value here. So phi 1 yt minus 2 plus ut minus 1 plus ut. Then again, if we take the second leg here, so we can write this yt minus 2 is equal to phi 1 and yt minus 3 plus ut minus 2. So in place of yt minus 2, we can write the equation phi 1 into yt minus 3 plus ut minus 2. So again, this equation we can write phi 1 square into phi 1, that is phi 1 cube yt minus 3 plus phi 1 square ut minus 2. This phi 1 multiplied this, then the remaining part comes here. If we use successive substitution, then we can write that up to n substitution, that is phi 1 to the power n yt minus n. Now in this part here, we have first you have written this particular term here, then successively backward series we have written here. So in this form we can retain this equation with the successive n substitution. This can be written as phi 1 to the power n yt minus n. Then we have used the summation for this whole equation. We can write I starts from 0 and goes up to n minus 1, phi 1 to the power I ut minus 1. So that means an AR1 process of this can be written as like this. So basically, if we observe this equation here, this has the two part. So one part, this which is a deterministic part, that is it depends on the initial observation of y0, and another we have which is basically stochastic part, that is the second part where it depends on the random term. So we can observe from this equation that this expansion basically represents yt in terms of the past value, that is yt minus n, and a series of lagged error terms, that is ut minus I, weighted by the powers of phi 1. So in fact, this process equation 2 consists the time dependent deterministic part, which is the first part, and stochastic parts, that is the second part. Then what is the stationarity condition for this AR1 process? So we know that this can be written in this. Now for the stationarity condition, what we know, for any series to be stationary, the moments of that particular series must be time independent. That is mean variance and covariance, what we have the concept of weakly stationary. Here let us say if we assume the absolute value of phi 1 is, let us say it is more than or equal to 1. So basically what we mean by the absolute value of this is more than or equal to 1, then the mean value of the process depends on the starting value of yt here. So that means it depends on the time. So the series cannot be stationary, the process cannot be stationary. On the other hand, let's assume if the absolute value of the phi 1 is less than 1, then the deterministic component is negligible if n is large, or in fact we can say if n tends to infinity, this becomes 0. On the other hand, this ut, for ut, this is nothing but a time independent, we have already assumed it. So that means the series becomes stationary when this absolute value of phi 1 is less than 1. So for this AR1 process, the stationarity condition is that the coefficient phi 1 in absolute value should be less than 1. For example, we can observe that phenomena in this particular graph. So here what we have assumed, the phi 1, the value is 0.7. Then we can see the stationarity, this series itself shows the series is stationary. Now let us say if the value of phi 1 is more than 1, let us say it is 1.1, then it shows a explosive behavior. As time passes, the series explodes. So this is explosive behavior, and from this clearly it is visible the series is non-stationary. So we can conclude for AR1 process, the absolute value of phi 1 must be less than 1 to be stationary. Now this autoregressive process of the different order we can, so again what is order? Order means the highest time lag associated with that particular process. So here yt, the AR1 process, that is yt is equal to mu plus phi 1 yt minus 1 plus u. So here the associated power is t minus 1. On the other AR2 process we can write like this, where the highest lag power is associated is 2, like here. Similarly we can write AR3 like this, and if we keep on continue, an ARP process, that is autoregressive process of order P, can be written like this. So that means an autoregressive process can be written in this. However, using the lag operator notation, we know that L of yt is nothing but yt minus 1. Similarly, L to the power p into yt is equal to nothing but yt minus p. This already we have discussed in the previous lectures. So that means we can write this order ARP process in concise way like this, that yt is equal to mu plus summation of phi I yt minus I plus ut, where I moves from 1 to p. Or in the lag form, we can write this equation like this. So here in the lag polynomial operator, we can write phi of L into yt is equal to mu plus ut, where the phi L is nothing but a polynomial function. So now what is the stationarity condition of a general AR autoregressive process for order P model? So though already we have discussed the stationarity condition for an AR1 process. So basically for the ARP process, the roots of this polynomial equation, that is 1 minus phi 1 z minus phi 2 z 2 z square minus phi, similarly phi 3 z 2 cube and up to phi p z to the power p is equal to 0. So basically the characteristic roots of this polynomial equation should lie outside the unit circle to be AR, for the AR autoregressive process of order P to be stationary. So for example, let us say the stationary condition of AR1 process in form of polynomial, how we can write? We can write 1 minus phi 1 z is equal to 0. Then we can say that if the roots is greater than 1, say the root of this is lambda, so it should be, absolute value should be more than 1. So it implies that absolute value of phi 1 must be less than 1. So the series is stationary. So however, it is necessary condition but not the sufficient condition. The sufficient condition is that the summation of all the characteristic roots also must be less than 1. So first, all the characteristic roots of this particular polynomial function must lie outside of the unit circle. The second sufficient condition is that the summation of all the parameters phi 1 should be less than 1. Then there is the very important theorem, what we know as the Walsh decomposition theorem. Though we have already shown that any autoregressive process could be represented into the two parts. One part will be the deterministic part, another part will be the stochastic part. So that we can write like this. So the Walsh decomposition, basically you specify the what will be the structure of the stochastic process, stochastic part. So the Walsh decomposition basically states any stationary series can be decomposed into the two unrelated parts. That is, one will be purely deterministic part and another will be a purely stochastic part, which will be in moving average process of the order infinity. In coming lectures, we'll be discussing about the moving average process. So from this decomposition theorem, we can say that ARP model could be represented into two parts. Already we have discussed. One will be the deterministic part, another will be the stochastic part. So let us discuss certain properties about the autoregressive process. So to discuss that, let's start with a simple autoregressive process that is of order 1. So we can write this. And for the simplicity, again, we are assuming the value of mu is 0 here, so that this equation turns out to be yt is equal to phi 1 yt minus 1 plus ut. From the equation 2, which already we have discussed here, that this particular equation could be represented in this particular form. Now, let us talk about the first property, that is the mean of the AR1 process. So this equation we will be representing this equation in these forms. So let's take the expectation of the both side of this equation. So once we take the expectation, it becomes expectation of yt and expectation of the deterministic part and expectation of the stochastic part. Now, since we have discussed that okay, the absolute value of phi 1 is less than 1 and this ut is a white noise process, therefore this phi 1 to the power n will tends to 0 and expectation of ut is 0. Now, in this equation what we can observe okay, here expectation of yt, if we take the phi 1 to the power n outside, then expectation of yt minus n. So since this part reaches to moves towards to the 0, that means 0 multiply the expectation of yt minus 1, so that is 0 plus expectation of ut minus 1 and summation, again it will be 0. So expectation of this AR1 process is nothing but equal to 0. So mean of an AR1 process without the constant is 0. Now let us calculate the second property, that is the variance of AR1 process. So AR1 process yt is equal to phi 1 into yt minus 1 plus ut. So using the Wahl's decomposition, this could be represented in this particular form here. Now let us say this, since absolute value of phi 1 is less than 1, so we can write this equation as yt is equal to ut, this plus phi 1 ut minus 1, phi 1 square ut minus 2 and so on here. Now we know that the variance of any variable here for the yt is nothing but the expectation of yt minus expectation of yt multiplied by yt minus expectation of yt. Already we have seen that in this case expectation of yt is equal to 0. That means variance of yt we can write expectation of yt into yt. Now we know that the value of yt could be represented in this form. So instead of yt we write this here, again for the yt we write this here. Now if we are multiplying these two parts, so what we have ut into ut square, then phi 1 square ut square, phi 1 square and phi 1 square, that is phi 1 to the power 4 and ut square minus 2 plus so on, plus the cross terms, that is ut and ut minus 1. So all this term basically includes, for example, it includes phi 1 ut into ut minus 1. Similarly, it also includes phi 1 ut minus 1 into ut. So all the cross terms is included here. So we can write like this. Now if we take the expectation here, since ut is a full white noise process with mean 0 and variance sigma square. So expectation of ut square is nothing but the sigma u square u. Phi 1 square expectation ut square minus 1 is nothing but the sigma u square. However, the expectation of all the cross product terms will be equal to 0 because it is a white noise process. So therefore all cross terms turns out to be equal to 0 and we can write like this. Or sigma square we can take common, plus 1 plus phi 1 square, phi 1 to the power plus 4. Since phi 1 is less than 1, so infinite sum of the above equation, that is using the geometric progression formula, we can write is variance of yt is nothing but the sigma square divided by 1 minus phi 1 square. So this will be the variance of yt. Now let's take the third property, that is the autocovariance. So the autocovariance of the first leg, that is here the autocovariance between yt and yt minus 1, we can write expectation of yt minus expectation of yt into yt plus 1 minus expectation of yt plus 1. Again we know that expectation of yt is equal to 0, so the case of expectation of yt plus 1. So we can write autocovariance, that is the gamma 1, autocovariance at lag 1, that is the gamma 1 is equal to this Or again, using from the previous information, we can write this equation like this. So in the similar approach, we can write phi 1 ut square plus phi 1 cube ut t minus 1 square, so on, plus the cross terms. Again, the expectation of the cross terms will be 0, and expectation of the square terms will be the sigma square. So we can write phi 1 square sigma square phi 1 cube sigma cube. Here we can take phi 1 and sigma square as a common, so that it remains. So if we take phi 1 sigma square common, so it remains 1 plus phi 1 square plus phi 1 to the power 4, so on. Again, using the idea that phi 1 is less than 1, so using the geometric progression, we can add this. So the autocovariance at leg 1 will be phi 1 sigma square upon 1 minus phi 1 square. Similarly, the second autocovariance, that is the second leg 2, we can write like this, and using the same rules as applied in the leg 1, we can write this equation like this. And here we will have phi 1 square sigma square common, and we can write this phi 1 square sigma square upon 1 minus phi 1 square. If we follow the same procedure, then we will have gamma 3, that is autocovariance as leg 3 will be phi 1 cube sigma square 1 minus phi 1 square. So basically, for any s leg, the general approach will be phi gamma s is equal to phi 1 to the power s into sigma square upon 1 minus phi 1 square. So this will be the structure of the autocovariance of an AR1 process. So once we calculate the autocovariance, then obviously we will be able to calculate the autocorrelation function. So basically, autocorrelation function is nothing, autocovariance divided by the variance. So we can write tau 0, that is autocorrelation function at lag will be gamma 0 variance divided by gamma 0, again that is variance, so it is equal to 1. And the tau 1, that is autocorrelation function at lag 1 will be gamma 1. So autocovariance at lag 1 divided by the variance, so ultimately we have phi 1, and tau 2, that is autocorrelation function at lag 2, is turned out to be phi 1 square. So tau 3 will be phi 1 cube. In fact, tau s, that is autocorrelation function at lag as s, will be phi 1 to the power s. So we can summarize this, that autocorrelation function can now be obtained by dividing the covariance by the variance. So we can have tau 0 is equal to 1, tau 1 is equal to phi 1, tau 2 is equal to phi 1 square. So at the successive legs, we have autocorrelation function like this. Now, what this reflects that the autocorrelation function for an AR1 process will be declining after having the maximum at lag 1, for which the value is 1. Why we say like that? Because we know that absolute value of phi 1 is less than 1. So this is the 1, phi 1 is, that is less than 1. If we square a value less than 1, it becomes further less and less. For example, if we have half, then if we square it becomes 4. If we square, then it becomes 1 upon 8. So basically, this is more than this and this is more than this. So as time passes, the autocorrelation function of an AR process declines. So that we can observe here. So when you can observe from this, let us say when the phi 1 is equal to 0.3. So here we can observe as time passes, the autocorrelation function at 0 was 1, and after that it starts declining. Similarly, you can observe here when the phi 1 is 0.6. So as the lag passes, here the autocorrelation function declines. And so is the case when the phi the value is 0.9. And similarly here we have when it is minus 0.3. So again we have the same phenomena. As time passes, the autocorrelation function starts declining. However, another thing you can notice, that lower the value of phi, the higher the speed of decaying. So here you can see it is quickly starts to moving towards 0. However, when it is close to 1, we can see it is decaying, but the speed of decaying is slow compared to 0 when the value of phi is less is smaller. So overall, two things we can observe from this. As time passes, the autocorrelation function of an AR1 process declines. However, the speed depends on what is the value of phi. Higher the value of phi, lower the speed of decreasing. Lower the value of phi, higher the speed of decreasing of ACF function. Then there is another concept of the partial autocorrelation function. So what we have observed in from the previous discussion that autocorrelation function of any stationary finite order AR process always converge to 0 but do not break off. So it converges to 0 in a sequential manner. As time passes, it moves towards to 0. Then for any AR process using the autocorrelation function, it becomes difficult to distinguish between the autoregressive process of different order. The solution for this problem is the partial autocorrelation function. So what is the partial autocorrelation function? As we have discussed in the previous lectures, it measures the correlation between an observation k periods ago and the current observation, taking account or after controlling the intermediate lags. So and this PACF helps us to find out the autoregress process, usually denoted by tau kk. So basically we can say partial autocorrelation function at lag k here. For example, the PACF for the lag 3 would measure the correlation between the yt and yt minus 3, removing or the controlling the effect of yt minus 1 and yt minus 2. So in general, for an autoregressive process of order P, there will be direct connection between yt and yt minus s where s is less than p, but no direct connection between for s more than p. So what we mean by this, let us say we have a AR2 process, that is yt is equal to phi 1 yt minus 1 plus phi 2 yt minus 2 plus ut. So what is the PACF? PACF is that the yt and yt minus 1, the correlation between these two. Since there is no intermediate lag, so it will be same. So the tau 1 is the same as the autocorrelation function here. However, the correlation at yt and yt minus 2 is based, this partial autocorrelation function here is basically the correlation between yt and yt minus 2 remove after controlling the effect of yt and yt minus 1. So there will be the direct relationship between yt and yt minus. However, there will not be any direct relationship between yt and yt minus 3. So that's what we mean. If the lag we are taking less than the order of the autoregressive process, then there will be the direct connection. However, if you are taking the lag beyond the order of the autoregressive process, then there will not be direct correlation. That means if there is no direct correlation, then the partial autocorrelation function should be equal to 0. So that means if the data generating process is an AR1 process, we have tau 11 is tau 1, then the tau 22 will be equal to 0. In fact, for any k more than 1, it will be always equal to 0. Similarly, for the AR2 process, tau 1 will be tau 1 and tau 22 will be tau 2 minus tau 1 square upon 1 minus tau 1 square. However, tau kk, where k is more than 2, it will be 0. So what we can say, thus for any finite order autoregressive process, the partial autocorrelation function provides the possibility of identifying the order of the process. How we identify? Okay, the last leg where the partial autocorrelation function is not equal to 0, that should be the leg of that AR process. If let us say for an AR process, partial autocorrelation function after 3 leg becomes 0, that means the order of that autoregressive process should be considered as 3. So for the similarly for AR process, we can say all partial autoregression coefficients of order higher than the P are 0. For example, here we can observe this is AR1 process. The series looks like this. Autocorrelation function, it will start declining as time passes. It moves towards 0. And here, however, PACF, what we can say, because it is AR1 process, at lag 0, we have 1, but after that, all are 0. So here, this is basically the confidence interval. So all these within this is basically considered as 0, equivalent to 0. So here, after certain, it becomes, this will be considered as nothing but the 0. So here you can see it basically becomes 0. Similarly, for AR2 process, we can observe this ACF starts declining. However, this we can have, see this after the 2 lag here, 1 is there and 1 is there, it becomes 0. And similarly for AR3 process, we can observe this 3 PACFs are non-zero and all other PACFs are 0. So looking the number of non-zero PACF, or by observing the number of non-zero PACF, we can guess the order of the autoregressive process. So from this discussion, we can note 2 points. That one point regarding the relationship between autocorrelation function and partial autocorrelation function with AR process, that as autocorrelation function will decay slowly, it will decay it will decay towards 0. It will decay towards 0. Second, the rate of decay will depend on the value of 5. Second, the partial autocorrelation function will cut off after the lag of autoregressive process, what we call order of autoregressive process. So once, let us say it is autoregressive process of order 3, then after third, the partial autocorrelation function becomes 0. So today we have discussed about what is autoregressive process, what are the stationary conditions of the autoregressive process, what are the different properties of the autoregressive process. In the next lecture, we will discuss about the second common process, that is the moving average process. Thank you so much. See you in the next class.